Welcome friends, Igor is here, and in this video we will talk about applications of linear algebra to balancing systems of weights. Let's get started. Suppose we have several objects in space and each of these point objects has a certain weight. The position of each such weight can be described by a vector that starts at the origin and ends at the point of that weight. Then the center of mass of this system of weights can be computed as the weighted average of the position vectors. The physical meaning of the center of mass is this: we can support this entire system at this one single point and the system will be balanced. So let's learn how to compute centers of mass and how to balance such systems of weights. In the first example, we have a system of three weights and we need to find its center of mass. So the three weights are 5, 6, and 2 kilograms respectively, and we write three position vectors, one vector for each weight. We can now compute the center of mass of this system as a weighted average of three position vectors. We use the given data to compute the value of this expression, and this expression is a scalar multiple of a linear combination of columns. First, we scale each position vector by the corresponding weight, then we add all the position vectors, and finally, we scale the total position vector by the inverse of the total weight. This position vector gives us the coordinates of the center of mass of the system. In the second example, we have a thin triangular plate of uniform density of total mass 3 kilograms. The balance point of this plate can be computed as a center of mass of a system of three weights which are located at the vertices of the triangle and all the weights are equal. In other words, we have a weight of exactly 1 kilogram at each of the three vertices. So we write the values of the weights and the position vectors for each vertex. We compute the center of mass of the system of these three weights as the weighted average of the position vectors. We use the given data and then we compute the value of the linear combination, which we then need to scale by the inverse of the total weight of the system. This computation tells us the location of the center of mass of the system of these three weights, which is then the balance point of this triangular plate. But now suppose we need to move this center of mass to another point. Let's say we would like to change the system in such a way that the center of mass of a new system is now located at the point 2, 2. To do this, we are allowed to add a total of extra 6 kilograms of weight, and we need to figure out how to distribute this weight among the three vertices. In the usual mathematical fashion, we will use x1, x2, x3 to denote the unknown quantities of additional weight placed on each of the three vertices. Then the new weight at each vertex is equal to the original weight, which was 1 kilogram for each vertex, plus the additional weight that we now put. We also have a constraint that the sum of all the added weights must be 6 kilograms. Also, the center of mass of the new system must be located at the point 2, 2. Let's figure out the values of x1, x2, and x3 that make this possible. We start by writing the center of mass equation. The new center of mass corresponds to the direction vector with components 2 and 2, and we write the new values of weights. Now we start simplifying the expression. First, we take scalar multiples of all the vectors. Also, let's observe that all the additional weights add up to 6. And by scaling both sides by 9, we arrive to the following vector equation. This vector equation plus the original constraint on the total amount of added weights allows us to write a system of three linear equations in the variables x1, x2, and x3. To solve this linear system, we write its augmented matrix and we apply the Gauss-Jordan elimination to obtain the reduced row echelon form of the augmented matrix. From the reduced row echelon form, we see that this system of linear equations has a unique solution. x1 must be equal to 3.5, x2 must be equal to 0.5, and x3 must be equal to 2. In turn, this means that we need to add 3.5 kilograms to the first vertex, and so the new weight of the first vertex is 4.5 kilograms. We need to add 0.5 kilograms to the second vertex, and the new weight of the second vertex becomes 1.5 kilograms. And we need to add the weight of 2 kilograms to the third vertex, and the new weight of the third vertex becomes 3 kilograms. In this case, with this new allocation of additional weights, the center of mass of the system is located at the desired point. And this is how we can use linear algebra to solve quickly and efficiently problems involving balancing systems of weights. If you found this video useful, and I hope you did, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. I hope to see you later infinitely many times. Have a great day.